Welcome back. So, in the last class we were looking at the concept of principal stress, and then we have actually written that the traction vector can be written as sigma times. So, the sigma is our stress tensor times n is the normal vector to the surface on which you are actually trying to find out the traction, right. And then so that sigma can be written as sigma times n, traction T can be written as sigma times n, and if the traction vector, or also it is sometimes it is also referred to as stress vector, which is also certain textbooks in the mechanics literature also refer to this traction vector as stress vector. So, if the stress vector or traction vector is parallel to the normal unit vector, then the T can be written as some constant times normal unit vector n, and we know that traction is sigma times n. Then this can be casted as an eigenvalue problem, whereas sigma n equal to lambda times n, that is like similar to our Ax equal to lambda x problem. This is what we call, we are familiar with this such a problem, called an eigenvalue problem. And then when we write that, the solution of the this equation requires, so the statement, this statement requires that this matrix be singular, which is nothing but the determinant of this matrix. So, the determinant of sigma minus lambda I must be equal to 0 for this statement to be true, right. So, that is what we have written here, and then we write the characteristic equation. The roots of this characteristic equation are the eigenvalues of the system, and they in turn represent the principal stresses of the stress tensor that we are looking at. And we introduce another concept called stress invariants, like for instance, if you take a vector, and if you for instance if in 2D, if you take a vector v, let us say which is 2 units projection onto x axis and 1 unit projection onto y axis. So, the vector v can be written as 2 1 with respect to this x and y axis. But now let us say that I am defining a new axis system, that is my x dash y dash. With respect to x dash y dash, I can write v equal to square root 5 and 0, right, because this is the magnitude of the vector. So, you can see that the same vector with respect to the original coordinate system, xy coordinate system is represented as 2 1, and the same vector in a new coordinate system is represented as root 5 comma 0. So, in these two systems we are representing two coordinate system, we are representing the same vector, but the elements of the vector are different, right, and hence you see you might think that they are actually two different quantities, but they are not. Only what we have changed is the frame of reference with which we are looking at this vector. However, in both the frames of reference, certain quantities do not change. What are those quantities? For instance, the length of the vector in this frame of reference and this frame of reference remains the same. So, that means the length is an invariant of your vector. Similarly, if you take a second order tensor, you can define invariants to second order tensor. That means irrespective of the frame of reference with respect to which you are writing your components of your stress tensor, certain quantities remain invariant, that means they do not change. So, for a second order tensor you will have 3 invariants, they are called represented as I1, I2, I3, right. So, I1 is basically the trace of your stress tensor, trace is nothing but sum of the elements on the diagonal. So, that is what is called your first invariant. So, that means the trace of the tensor does not change by coordinate transformation. And the second invariant is sum of the principal minors, and the third invariant is the determinant of the tensor. So, these three things do not change under coordinate transformation. Okay. So, this is what we mean by stress invariants, and we will use them in the failure theories, and that is why we are introducing the concept of stress invariant. So, basically what it means is that whether you work with full stress tensor or a principal stress tensor, you can write your failure theories in terms of these invariants, okay, I1, I2, I3, or in terms of principal stresses. Alright. So, for instance, if you take stress tensor in principal coordinate frame, in the principal coordinate frame you will only have normal stresses and the shear stresses will be 0, and hence you will only have diagonal components sigma 1, sigma 2, sigma 3. So, from this we can see that the first invariant is sum of the elements on the diagonal, that is the trace of the tensor, and the second invariant is the sum of the principal minors, and the third invariant is the determinant of the stress tensor. So, even if you express the stress in a different frame of reference and then you may have full stress tensor, that means all the elements may be non-zero, even then for that particular strength tensor these three quantities should remain the same, that is what is the meaning of invariant. Alright. Now, the question is the following, and we try to answer this question towards the end of today's lecture. Okay. So, you are given two different states of stress, that is sigma equal to 10 0 0 0 5 0 0 0 5 in principal frame of reference, and this is also given in principal frame of reference, and which of these stress state is likely to cause yielding first, meaning which of these stress states would cause yielding first, either this one or this one, right. So, think about this and then we will see by looking at this looks like it has higher values of the stress. So, it is possible that this is probably going to cause yielding first, and but let us see is that the right answer or not towards the end of this discussion. Okay. So, this now we will start discussing about the distortion energy theory. So, the microscopic yielding that we have discussed in the mechanical behavior module is due to relative sliding of atoms within the lattice structure, right, and the sliding is caused by shear stress, or in other words the plastic deformation is caused by dislocation motion, which is accompanied by the distortion of the shape of the shape of the part. That means, whenever you are having shear deformation or the sliding of atom planes one past the other, you have distortion of the crystal lattice, or there is a shape change to the crystal lattice or the part. So, the energy stored because of the work that you are doing by applying external forces is the energy, because of that work there is some energy stored in the material. So, the energy stored in the material from the distortion part just by shearing is an indicator of shear stress present, right. So, because that is what is causing the deformation, the plastic deformation. People were earlier thinking that is also a basis for the total energy strain energy theory. People were thinking that total strain energy stored in the material causes yield failure, that means that is what causing plastic deformation or the onset of plastic deformation, that is what people were thinking. So, when we are looking at what do we mean by total strain energy, so the area under the curve up to yield point, let us say sigma I is our yield point, and corresponding strain is epsilon I, the area under this area of this triangle is what we call total strain energy. However, experiments proved them wrong. So, they saw that it is actually not the total strain energy that is responsible for distortion or the plastic deformation. So, the total strain energy density, assuming linear stress strain relation up to yielding, is 1/2 sigma times epsilon for a one dimensional case, but if it is in full 3D you can write that as half sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. It is good to work in principal frame of reference, so that it is much easier to write this expression, right. And you know the in 3D the stress strain relations can be written using this formula. So, epsilon 1 is equal to sigma 1 by E minus nu times sigma 2 by E plus sigma 3 by E, and epsilon 2 and epsilon 3. Again we are writing in the principal frame of reference. Now, you can plug in the value formula for epsilon 1 into this equation for total strain energy, and then you will be able to write your total strain energy U in terms of sigma 1 E and nu as shown here. This is basically, this equation is obtained by plugging in the values of epsilon 1, epsilon 2, epsilon 3 in this equation, you will get that equation, that is your total strain energy. So, now let us talk about the concept of hydrostatic loading. So, because that is going to be useful for us to understand how materials actually plastically deform under the action of a total stress. Okay. So, it is found that a very large amount of energy can be stored in a material without failure if it is hydrostatically loaded. What do you mean by hydrostatic loading? Applying hydrostatic state of stress means having the normal stress in all the 3 directions being equal, right. Sigma 1, sigma 2, sigma 3 of if sigma 1 equal to sigma 2 equal to sigma 3 is equal to some constant sigma, then such a state of stress is called hydrostatic state of loading, right. So, if you have this kind of a loading, then the material can be loaded with such a state of loading without actually having to plastically deform. That means, you can store large amount of energy without failure. This is possible because this uniform stress state is there in all the 3 directions, x direction, y direction and z direction. You have a uniform stress, and because of that you will not have any shape change, right, because it is only size change. The size will be reducing, but the shape remains the same because of the uniform stress in all the 3 directions. So, materials can actually be hydrostatically stressed beyond ultimate strength in compression. If you are only applying hydrostatic stress, they can be stressed beyond ultimate strength in compression. So, Bridgman did an experiment. We have discussed the Bridgman correction when we are discussing the stress strain curves, right, the Bridgman correction that we have discussed about it. So, the same person has actually done an experiment on ice, where he has subjected ice to solid ice to 1 mega pounds per square inch, extremely high hydrostatic pressure, hydrostatic compression without failure. The material did not fail even at such very high compressive loads, whereas normally if you are not subjecting it to hydrostatic compressive loads, it is much easier to break the ice, right. So, the hypothesis is that the uniform stress in all directions creates only volume change, but no distortion. Distortion means shape change. Because why we are talking about shape change? Because the plastic deformation is nothing but relative shearing of atom planes, which is nothing but shape change. So, if you are applying uniform stress in all the 3 directions, you cannot import this shape change, but you can only import volume change. That means, size may reduce, but remains the shape becomes invariant, the shape remains the same. So, think about the how do you plot the how does your Mohr circle look like for a hydrostatic state of stress, because you are saying sigma 1 equal to sigma 2 equal to sigma 3. So, the radius of your Mohr circle will be 0, right, sigma 1 minus sigma 3 is equal to 0, or sigma 1 minus sigma 2 equal to 0, sigma 2 minus sigma 3 equal to 0. So, the radii is 0, and hence your Mohr circle will be a point on which axis? A point on sigma axis or tau axis? It should be a point on sigma axis, because it is only a state of pure normal stress, right. Hydrostatic stress is a normal state of stress. Alright. So, the total strain energy that you are storing in a material can now be decomposed into 2 parts, the hydrostatic energy and the distortion energy. So, the energy that is responsible for size change or volume change, the energy that is responsible for shape change. Okay. So, it is sigma UH plus UD. Now, the sigma 1 that we are talking about, the normal stress, principal stress, maximum principal stress sigma 1, sigma 2, sigma 3, all the sigma 1 can be written as a hydrostatic part and a deviatoric part. This part is called deviatoric part, which is responsible for shape change. Sigma 2 will be again, because when we are saying hydrostatic part, the hydrostatic part should be same in all the 3 directions. That is why I am writing sigma h, sigma h, sigma h. It should be same, only then it is called hydrostatic part. So, out of sigma 2, sigma h plus sigma 2d will be, sigma 2d will be your deviatoric part, and sigma 3d will be your deviatoric part. Then you can write that sigma 1 plus sigma 2 plus sigma 3 is equal to 3 sigma h plus sigma 1d plus sigma 2d plus sigma 3d, right. I am just adding up these 3 guys. Then we can write 3 sigma h is equal to sigma 1 plus sigma 2 plus sigma 3 minus sigma 1d plus sigma 2d plus sigma 3d. Now, if you do not have any distortion, if you only have volumetric change, then this term can be made 0, and as a result your hydrostatic stress will be equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So, if you have a stress tensor sigma 1 0 0, 0 sigma 2 0, 0 0 sigma 3. This can be written as sigma 1 plus sigma 2 plus sigma 3 by 3, that is your hydrostatic stress. Sigma 1 plus sigma 2 plus sigma 3 by 3 plus the deviatoric part, that is sigma 1 minus sigma h. What is sigma h? That is that, right, 0 0 sigma 2 minus sigma h, 0 0 0 sigma 3 minus sigma h, and this is what we call hydrostatic part of the stress tensor, and this is the deviatoric part of the stress tensor, and this is what is responsible for volume change, and this is responsible for shape change. All right. So, now I can calculate the strain energy due to, because we have said the total strain energy is hydrostatic energy plus distortion energy, right. So, hydrostatic energy can be calculated using the same formula that we have derived here. When we are talking about hydrostatic energy, then sigma 1, sigma 2, sigma 3, all three of them will be same. So, that is what we are writing, sigma 1, sigma 2, sigma 3, all of them are same, and then your hydrostatic part of energy turns out to be this simple expression 3 by 2 into 1 minus 2 nu by E sigma h square. And here nu is our Poisson's ratio. Please note that we are always here we are discussing about isotropic materials, we are not discussing about anisotropic materials, isotropic materials. That is why there are only two elastic constants nu and E. So, your hydrostatic stress can be written as sigma h square, and sigma h is again sigma 1 plus sigma 2 plus sigma 3 by 3, and plugging that in here will actually give you your hydrostatic energy in terms of your principal stresses, sigma 1 square plus sigma 2 square plus sigma 3 square plus 2 times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, and there will be 9 here, and this 9 cancels 3 times, and 3 to 6 will be there. So, that is why this is the expression for your hydrostatic part of the energy when you have a stress tensor in principal stress space, and the distortion energy will be total strain energy minus hydrostatic part of the energy. We have already calculated the total strain energy minus the hydrostatic part, that is what gives us distortion energy, right. And this distortion energy is what is responsible for plastic deformation. The hydrostatic part is not responsible, and hence whenever we are going to assess plastic deformation, we should subtract this hydrostatic part of the energy and only consider the distortion part of the energy. So, that is why the distortion energy is calculated that way. So, if you simplify this equation, the distortion energy is given by this simple expression. So, now this is the distortion energy for a full 3-dimensional state of stress, and to check for failure, what we need to do is we compare the distortion energy per unit volume, that is this equation, with the distortion energy per unit volume in a tensile test specimen at failure, right. When you are doing uniaxial tension test, that is when you are actually measuring yield strength, right. So, you measure the distortion energy that is stored until the yield point in your uniaxial tension specimen with the distortion energy of this 3-dimensional state of stress. So, when you are talking about uniaxial tension test, you can clearly say that sigma 1 is non-zero and sigma 2, sigma 3 are zeros. So, in this expression, if you put sigma 2 and sigma 3 0 and sigma 1 is equal to sigma y, because that is the distortion energy stored at the yielding of uniaxial tension specimen. So, then you will get u dy, and then because sigma 2, sigma 3 are 0, in this equation if you plug in this condition into that equation, this becomes 0, this becomes 0, and that becomes 0, this becomes 0, that becomes 0, and as a result 1 plus nu by 3 e times sigma y square, because sigma 1 equal to sigma y at the yield point of the material. So, this is our distortion energy for the uniaxial tension specimen, right. So, by looking at the property of the uniaxial tension specimen's energy, so now we are comparing energies. So, that is a good situation, because we are not these two are scalars. So, by when we are saying that when the distortion energy stored in a material because of a complex state of loading becomes equal to the distortion energy stored in the material subjected to uniaxial tension test at the yielding, that is when the material subjected to compressed state of loading also undergoes yielding, right. That is the failure theory given, that is the statement of distortion energy theory. So, the material is safe as long as the distortion energy stored in the material under complex state of stress is less than u dy, and the failure happens when u d becomes equal to u dy. U dy is the distortion energy at yield point for the uniaxial tension specimen, and then that means basically you equate these two guys, and then this is our statement for distortion energy theory. So, this is the mathematical expression for the distortion energy theory, and so less than or equal to means if it is less than, then our material is not yielding, and if it is equal to, then that is when we say that the material is yielding. So, if you write this expression as square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus, so if you write this guy as sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 is equal to sigma y square, that represents the boundary of your failure surface. So, within that boundary your material is safe, outside the boundary or on the boundary the material is unsafe. Alright. So, now let us take a simple case of loading called pure shear. When we are calling pure shear type of loading, we know that the condition for pure shear is sigma 1 equal to minus sigma 3 is equal to some constant, the shear stress, maximum shear stress, and sigma 2 equal to 0. That is the meaning of pure shear loading. So, for pure shear, that means when you are applying torsion, you plug that in your expression here. So, sigma 1 equal to minus sigma 3, so and sigma 2 equal to 0. So, this becomes 0 and that becomes 0 and this becomes 0, only 3 terms will remain, square root of sigma 1 square plus sigma 3 square minus sigma 1 sigma 3 is equal to, so I am squaring on both sides. So, sigma y square is equal to sigma 1 square plus sigma 3 square minus sigma 1 sigma 3, and sigma 1 square is tau, sigma 3 square, so tau max in fact, right. If you are drawing the, that is our Morse circle, and that is my sigma 1 and that is my sigma 3 and that is our tau max, right. So, this comes out to be sigma 1 equal to minus sigma 3, that gives you 3 sigma 1 square, and we know that sigma 1 equal to tau max. So, 3 tau max square, right. So, what basically it means, if you are writing sigma 1 is equal to sigma y square, right. So, sigma 1 is equal to sigma y by root 3 or 0.577 times sigma y. That means, when you are applying pure shear loading, if your principal stress becomes equal to 0.577 times the uniaxial yield strength of the material, not actually equal to the uniaxial yield strength of the material, right. It is actually going to yield when the principal stress is only 0.577 times the yield strength of the material. So, yield strength, whenever you say, it is a uniaxial tension test yield strength, that is when failure happens, or when the shear stress, when the maximum shear stress in a material, at any point reaches 0.577 times the yield strength of the material, that is when yielding happens or failure happens. Here when we say failure, we are actually meaning onset of plastic deformation. So, which otherwise means that the shear yield strength of a ductile material is 0.577 times the tensile yield strength of the material. So, shear yield strength is equal to 0.577 times tensile yield strength. So, as we have already discussed, this is the distortion energy theory is a failure theory that is applicable for ductile materials, which actually show yielding, right. It is not really a good theory for brittle materials. So, the ductile failure from distortion energy theory. So, failure in case of ductile materials in static tensile loading is considered to be due to shear stress. Alright. So, the statement of distortion energy theory, the mathematical statement of distortion energy theory is this, which basically represents the surface boundary of your failure surface. In 2D, when we are making sigma 2 equal to 0, that means plane stress case, then we will see that sigma y is equal to square root of sigma 1 square plus sigma 3 square minus sigma 1 sigma 3. So, if you would plot this, so this is something that we know, this is a material property, it is nothing but say square root of sigma, the equation is square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 3 is equal to some constant. This constant here happens to be yield strength of the material, okay, is a constant, and that is actually equal to yield strength of the material. So, this is similar to our general form of our failure theory, f of sigma equal to 0, right. How can we write that? Square root of sigma 1 square minus sigma plus sigma 3 square minus sigma 1 sigma 3 minus sigma y equal to 0. So, that is our f of sigma, right. This is a general form. For distortion energy theory, that f of sigma happens to be square root of sigma 1 square plus sigma 3 square minus sigma 1 sigma 3 minus sigma y, or sigma 1 square plus sigma 3 square minus sigma 1 sigma 3 minus sigma y square. You can also write that way. So, if you would plot this particular function in sigma 1 sigma 3 space, that means if you take your x axis to be sigma 1 and y axis to be sigma 3, then you can plot this function, right, because you know the value of sigma y. Then how does it look like? It is basically an equation of an ellipse. This actually represents the equation of an ellipse, which looks something like this, okay. And you can clearly see that if you are applying uniaxial loading, that is basically the failure happens when sigma 1. So, I am normalizing my sigma 1 and sigma 3 with Sy is my sigma y, Sy and sigma y are same. So, yield strength of the material both are same, okay. So, sigma 1 by Sy becomes 1, that is when failure happens, when you are having uniaxial tension, right. But please note that there are points at which here this distance from here to here is actually longer than this distance is larger compared to this distance. That means, if you are loading in this fashion, you have much more room for failure to happen. And here you can see this is our sigma 1, this line on this line, this dashed line represents sigma 1 equal to minus sigma 3, and that represents our pure shear loading, and then we will see that this corresponds to 0.577 times sigma y, that point corresponds to 0.577 times sigma y, okay. This is the pure shear case. So, that is the equation of an ellipse. So, the how does the distortion energy theory equation looks like in a 3-dimensional space where your axes are sigma 1, sigma 2 and sigma 3. So, the 3D distortion energy equation describes a circular cylinder inclined at Euler angles 45 degree to the principal stress axis, and interior of that cylinder is safe region against yielding. So, even here all the yellow region is safe, and the red is the boundary at which it is actually not safe, and the moment your stress state falls outside, that means it is already yielded beyond yield stress, right, which is not a good thing. So, you should ensure that whenever you are designing a component, your stress state when you are representing on sigma 1 sigma 3 plane should be within this boundary of the red curve. So, it should be always within the yellow region. So, the for a 3D states, in 2D it looks like an ellipse, and in 3D it looks like a cylinder, a circular cylinder inclined at Euler angles 45 degrees to the principal stress axis. So, the axis of the cylinder in that case describes the locus of all hydrostatic stresses extending to plus or minus infinity. That means, on the hydrostatic stress you can see. So, this is how your forget about that hexagonal shape that is shown there, but focus on the circular cylinder, and you see that this is the axis. Here you have your sigma 1, sigma 2 and sigma 3, and your cylinder is inclined at a 45 degree angle with all the principal axis, and this line that you are seeing here represents a state of stress on which sigma 1 equal to sigma 2 equal to sigma 3, and you see that on that line, as long as your stress state is on that line, it will never intersect the boundary, right. That means that is actually the hydrostatic state of stress. That means the failure, the distortion is not caused by this hydrostatic stress, and so this is called, this yield surface is called von Mises yield surface after von Mises, who is responsible for this distortion energy theory. Okay. So, the intersection of this, if you see this, the intersection of that cylinder with each of the principal axis is an ellipse as shown in the 2D case. So, if you take the intersection of this cylinder, if you cut the cylinder with respect to one of the axes, then you see that it is going to be an elliptical shape, right, and that is the shape that you are actually seeing in the 2D case. Okay. So, the distortion energy theory, the failure surface or the yield surface, that is also called yield surface, is a ellipse on sigma 1 sigma 3 plane inclined at an angle 45 degree, and in 3D it is a circular cylinder inclined at 45 degree Euler angles to all the sigma 1 sigma 2 sigma 3 axes. Okay. So, that is about distortion energy theory. Now, this is a question that we have started off with, right. Which state of stress is likely to cause yielding? You say this is one state of stress, this is another state of stress. So, now if you look at, you calculate the hydrostatic part of the stress tensor and deviatoric part of the stress tensor, and you see that the second stress tensor can be written as the first stress tensor plus some hydrostatic part, right. So, this hydrostatic part, so you can clearly say this is 20 plus 15 plus 15, 50, right. So, you can write this guy like this, and so both will represent as a result, both will represent an equivalent state of stress corresponding to yielding, as the second state of stress is only an addition of hydrostatic stress to the first one. You are only adding an additional hydrostatic stress which does not cause yielding, and hence this guy and this guy will yield, will represent same state of yielding. So, if you would draw the stress state on sigma 1 sigma 3 plane, both of them will show the same point on your sigma 1 sigma 2 sigma 3 plane, because it is a 3D state of stress. All right. So, now the distortion energy theory equation, the states that this stress, which is a complex equation taking into account of sigma 1 sigma 2 sigma 3, it is a tensor with elements of the tensor principal stress tensor. This value is compared with a scalar value, sigma y yield strength is a scalar value, right, it is only one number. So, this is also a scalar. So, now what we can actually say, this value can be given a name called equivalent stress. So, this is what we call von Mises equivalent stress or von Mises effective stress, is defined as the uniaxial tensile stress that would create the same distortion energy as is created by the actual combination of applied stress. So, if you write sigma E equal to square root of this guy, that is basically what we are saying is this is equivalent stress, as if although you have a combined state of stress, right. So, this is equivalent to your one dimensional, if you are doing a one dimensional uniaxial tension test, what would be the stress that you would apply in order to have same amount of distortion energy as compared to this combined state of stress. So, that will be this guy. So, that is what we call equivalent stress. So, basically this equivalent stress is a scalar quantity, please keep that in mind, it is not a tensorial quantity, because it is a one dimensional equivalent of your combined state of stress. You can write this equivalent stress both in terms of principal stresses or using your full stress tensor, which is sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau xz. So, both the formula are possible, and you must have learned this in your strength of materials class or mechanics of materials class. So, when you are designing components, designers typically use something called factor of safety. That means they do not want to design their component such that it, under the action of external loads it is going to experience yield strength. They would want to design their component such that the component experiences a stress lower than the yield strength of the material, right. So, and hence they use a factor called factor of safety to ensure safety of design. So, the factor of safety in this case for the distortion energy theory can be written as sigma y divided by sigma e, where sigma e is our equivalent stress as calculated here and sigma y is our factor of yield strength of the material. So, the modified distortion energy theory statement compared to the previous long mathematical expression can be written as sigma y by n is equal to sigma e. So, if your equivalent stress reaches the value sigma y by n when you are taking factor of safety into consideration, that is when failure happens, otherwise the failure does not happen. All right. So, now let us also look at the deviatoric part of the stress tensor, that is also called stress deviator. So, the stress tensor sigma ij can be written as a sum of hydrostatic component and deviatoric component, right. So, the deviatoric stress tensor is usually represented with the symbol S. So, the full stress tensor sigma can be written as deviatoric stress tensor plus hydrostatic stress tensor, and so let us say the full stress tensor is sigma 1 1 sigma 2 to sigma 3 3, this is our full stress tensor, minus this is hydrostatic part, I am writing sigma h or pi, pi is basically sigma 1 plus sigma 2 plus sigma 3 by 3 or sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. Please note that sigma h can be sigma 1 plus sigma 2 plus sigma 3 by 3 or sigma xx or sigma 1 1 sigma yy plus sigma zz by 3, both are same. Why? Because we have just now in the beginning of this class we have discussed that the trace of stress tensor is invariant, that means what is trace? Sum of the elements in the diagonal. So, this is the trace and this is also trace, and hence these two should give you the hydrostatic state of stress. So, the deviatoric stress can be written as sigma 1 1 minus this expression, that is pi, I am calling that as pi. So, that is our deviatoric stress tensor or stress deviator. Okay. Now, let me try to write the invariance of the stress deviator. If you write the determinant of the stress deviator, that can be written as lambda cube. So, if you write characteristic equation, that can be written in terms of the invariance of the stress deviator. The stress deviators invariants are represented as usually with j, whereas I1, I2, I3 are the invariants of the full stress tensor, J1, J2, J3 are the invariants of the deviatoric stress tensor. So, that is lambda cube minus J1 lambda square minus J2 lambda minus J3, where J1 is the trace of the stress deviator. What is the trace of the stress deviator? We can clearly see, because it is a stress deviator, it will only cause distortion, no volume change, and the diagonal elements actually represents the volume change. So, if you calculate the trace, that actually makes it is equal to 0. So, always first invariant J1 is always 0, right, and the J2 is the second invariant of the stress deviator, that is given by this expression, and it is actually the I2 is the sum of the principal minors, J2 is not sum of the principal minors, but J2 is the negative of the sum of the principal minors, negative of the sum of the principal minors of deviatoric stress tensor, and J3 is the determinant of the stress deviator, and here we have written the relations between J1, J2, J3 and I1, I2, I3. J2 can be related to I1, I2 and J3 can be related to I1, I2, I3. All right. So, SKK is equal to 0 means the trace, the volumetric part is 0, which actually means that the stress deviator is in state of pure shear, because it is only creating distortion. So, now the equivalent stress or von Mises stress, this is also called von Mises stress, sigma E, is defined as, can also be written using this expression as sigma E is equal to square root of 3 J2, right, square root of 3 times J2 or square root of 1 by 2 in terms of this. So, the previous expression is also correct, sigma 1 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1, that is also correct, and this is also equivalent, right, you can write either way. So, if you know the second invariant of the stress deviator, then you can calculate the equivalent stress right away, as function root 3 as sigma 3 equal to square root of 3j2, alright. So, if you now look at this sigma ij, from that you can calculate the mean stress or hydrostatic stress to be 21/3. From that I can calculate my stress deviator, right. The stress deviator is basically this. Now, if you look at my sigma 1, sigma 2, sigma 3, that is principal stresses for the full stress tensor is 16, 4 and 1, and here you can also calculate principal stresses for stress deviator, only deviatoric part of the stress tensor -6, -3 and 9. And note that sigma 1 plus sigma 2 plus sigma 3, so S1 plus S2 plus S3, that is the trace of the stress deviator even in the principal frame of reference should also become equal to 0, that we can clearly see -6, -3 and plus 9 becomes 0, and I1, I2, I3, and you can see that J1 is equal to 0, J2 equal to 63 and J3 equal to 162, right. So, our sigma E now we can directly calculate root 3 J2, that is equal to square root of 3 times 63, that is square root of 189, right. Alright. Now, if you know the principal stresses, you can always find out principal directions, right. That means the eigenvectors will be the principal directions. If you know eigenvalues, you can always find the eigenvectors. So, the eigenvectors will be the corresponding principal directions for the eigenvalues or the principal stresses. And if you would use the principal directions to transform our sigma and S. So, let us say you are constructing a matrix Q for Q such that, let us say my principal direction V1, V2, V3, 3 vectors, this is the vector corresponding to lambda 1 or the sigma 1, this is the vector corresponding to sigma 2, this is the vector corresponding to sigma 3. Then if you write Q transpose sigma Q and Q transpose S Q, you do this transformation and see what you will get, okay. Alright. So, let us do this problem and try to understand about applied distortion energy theory to this. So, the stress analysis of a spacecraft structure gives the state of stress as shown in this figure. If the part is made from an aluminum alloy whose yield strength is 500 MPa, the question is, will this stress state cause yielding to the material? If not, what is the factor of safety? So, it is extremely important to write your sigma x, sigma y, tau xy with proper signs, right. So, this is our equivalent stress, because it is good to write in the XYZ frame of reference rather than writing in the principal frame of reference, because this is here we are given XYZ data, not the principal data, because you have a shear stress component here. So, that is not a principal state of stress. So, I am writing this in this way, and since sigma y, so this is sigma x and that is sigma y. So, sigma g, so that means x axis is in this direction, y axis is in this direction. So, g axis should be in this direction, positive g in that direction. So, sigma z is not when you are writing sigma z, it should be minus 50 MPa, because it is compressive. Normal, this is the direction of your axis, it is going in the negative direction, it should be compressive. So, that is why we are taking sigma z to be negative, right. And again tau yz, because here on this guy, if it is shear stress is positive, then that should have been like that, but here your shear stress is negative, because it is in the opposite negative z direction, and hence tau yz is also minus 30. This is important. If you do not take them to minus 30 and minus 50, you will get a different state of stress, different equivalent stress. That is extremely important to realize. So, you are getting your equivalent stress by this calculation to be 224 MPa. Since the sigma E, what is sigma y? 500 MPa. Since this value is less than sigma y, the component is safe, and the factor of safety is yield strength divided by the equivalent stress, and hence that becomes 500 by 224, that is about 2.23, that is our factor of safety.